This is an AS Further Statistics 1 question on chi-square tests using the Poisson distribution. A researcher is investigating the distribution of orchids in a field. He believes that the Poisson distribution with a mean of 1.75 may be a good model for the number of orchids in each square meter. He randomly selects 150 non-overlapping areas, each of 1 square meter, and counts the number of orchids present in each square. The results are recorded in a table below, so this table here. He calculates the expected frequencies as follows, and they're in this table here. Part A, find the value of R, giving your answer to 2 decimal places. Now I think the easiest way to calculate the value of R would be to subtract all of these values from 150, because we know that the sum of all the frequencies has to be 150, because that's given in the question. So if we did 150 and we subtracted all the values, 26.07 minus 45.62 and so on, that will give us a value of R equal to 1.36. The other way to work out R would be to calculate the expected probability for this cell, times it by 150 to get the expected frequency. So doing it that way, let's call our random variable X with a Poisson distribution and a mean of 1.75, and we want to calculate the probability that X is more than 5. That'll give us the expected probability, and that's equal to 1 minus the probability that X is less than or equal to 5, and that gives 0.009133 and so on. We need to times that by 150, and if we do so, we get R is equal to 1.37003 and so on. So to 3 significant figures, that would be 1.37. So you'll either get 1.37 if you calculate it using the probabilities. If you just take the sums of the values and subtract them from, or the sum of the frequencies and subtract them from 150, you will get a value of 1.36. The researcher will test at the 5% level of significance whether or not the data can be modelled by a Poisson distribution with a mean of 1.75. Part B, state clearly the hypothesis required to test whether or not this Poisson distribution is a suitable model for these data. Now, whenever you do these chi-squared tests, it's the only time that you would write your hypothesis, your null and alternate hypothesis using like a sentence. So here we want to see whether the Poisson distribution with a mean of 1.75 is a suitable distribution. So H0, whenever we're testing against a distribution, will be that this is a suitable distribution. So Poisson 1.75 is a suitable model, and H1 would be that this Poisson isn't a suitable model. So I'll just put is not a suitable model. The test statistic for this test is 2.0, and the number of degrees of freedom to be used is 4. Part C, explain why there are 4 degrees of freedom. Well, I guess if we first look at this, we've got 1, 2, 3, 4, 5, 6, 7. So you might think, oh, 7 degrees of freedom. But whenever the expected frequencies are less than 5, we need to combine them so that they become more than 5. So at the moment, I've got this cell here. Okay, that expected frequency is less than 5. So we'll combine it with the cell next to it, that one. So if we add together 3.57 and 1.36, that only makes 4.93. So combining these two columns still doesn't give us an expected frequency greater than 5. So in fact, we've got to combine these 3 columns to ensure that we get an expected frequency greater than 5. So we'll write that down first. So we need to combine cells where the expected frequency is less than 5. So we need to combine the last 3 columns. So we need to say something about the totals agreeing. So once this has been combined, you can see that leaves us as 1, 2, 3, 4, 5 columns. But since we only need 4 values to find the 5th one, because we know what the total is going to be, that gives us 4 degrees of freedom. So I need to put that in words as well. So we can continue to say we then need to subtract 1 from 5. That's because we've got 5 columns remaining after combining, since the totals agree. So I guess I could write down that 5 minus 1 equals 4. But just writing 5 minus 1 equals 4 won't get you the mark. You need to talk about combining, and it's important that you use this phrase about the totals agreeing. Okay, part D, stating your critical value clearly, determining whether or not these support the researcher's belief. Okay, now there's not going to be a lot of work to do because we've already got our test statistic here, 2.0, so we don't need to do any calculation. So it's just about looking up the critical value in the formula book or getting it on your calculator and then comparing it with this test statistic, and that will then allow us to determine whether or not this supports the researcher's belief. So I already know that I've got 4 degrees of freedom, and we are testing at the 5% level of significance. So I'm just going to grab a formula book and look up that value, and that gives us a critical value of 9.488. Now we compare that value to our test statistic, and 2.0 is less than 9.488. So you could think of it as the spread from our data calculated is less than a critical value. So that allows us to accept H0. Now we don't need to talk about accepting H0 and it being a suitable model. We can just refer to the fact and talk about the researcher's belief. Does the data support his belief? His belief is H0, that this data can be modeled with a Poisson distribution. This supports his belief. Yeah, so that's all we need to say. Okay, so that's all we need to do. This supports the researcher's belief because his belief has already been stated and we don't need to state it again. The researcher works in another field where the number of orchids in each square meter is known to have a Poisson distribution with a mean of 1.5. He randomly selects 200 non-overlapping areas, each of 1 square meter, in this second field and counts the number of orchids present in each square. Part E, using a Poisson approximation, show that the probability that he finds at least 1 square with exactly 6 orchids in it is 0.506 to 3 decimal places. Okay, so I'm going to state my random variable. I put it in red because you don't need to write this down. I'm going to say let x equal the number of orchids in each square. So that tells me that what I want to do is to find a probability that is exactly 6. So x is this Poisson distribution with a mean of 1.5. So if I work out this probability on my calculator, so this is basically the number of finding exactly 6 orchids in one of these squares, and that is 0.0035299, and then I think it's 88 after that. Now we'll get on to this bit about 200 non-overlapping squares. I'm going to use the letter Y. This would be binomial because we've got 200 squares, and the probability that I find exactly 6 in one of those squares is the probability that I've just worked out. But what we're doing is we're using a Poisson distribution, and we can do that because n is large, greater than 50, and p is small. So this is the Poisson approximation part. Now remember, if we want to do a Poisson approximation of a binomial, then the way that we find lambda, that's equal to n times p. So this will be 200 times by 0.00352999, and what that gives us is 0.7059977, and so on. Now we've got this bit here. So show the probability that he finds at least one square of exactly 6 orchids. So at least one square means at least that, at least one or more, which is equal to 1 minus the probability that it's less than or equal to 0. Now less than or equal to 0 is actually equal to 0. We can do it either way, so you could put just probability x is equal to 0 because it isn't going to be anything else. So now we're going to use our calculator to work out what this is. So it's going to be 1 minus, and this is 0.49361, and so on. Now this is using this approximation here, so using this value of lambda, and if I work that out, I get, let's have a look, just do 1 minus that number, and that is 0.506, let's write it down, 5063, and that continues, and we just needed to show that it was 0.506 to 3 decimal places, which it is. So 0.506 to 3 dp as required.